Hello, so in this video we're going to be talking about harvesting still, but we're going to talk about harvesting with the logistic model. Last time we talked about harvesting using the exponential model. Now we're going to use the logistic model and use harvesting kind of term involved. So remember what I talked about with harvesting. Harvesting is just simply, you know, if you remember, I tried to get a picture into your head of, you imagine you harvest a field on a late late summer's day, and you go out and you basically pick all your crops. So what you're fishing something, you're taking fish away from the population. So basically what harvesting does is it takes into account of immigration and emigration. Really simple way of taking into account immigration and emigration. And if you remember, you go out, so you had rate of change of population is equal to a population times some growth rate. Okay, but because now we're taking into account harvesting, so in other words, things are being taken in and out of the system, which don't account for growth rates. So in other words, births and deaths. Okay, we have to take into account harvesting, so that takes into account immigration and emigration. And like I say, remember the picture which I tried to get into your head. You're going out into, you have a field full of crops, and you go out and you harvest the crops. So in other words, you're taking the crops away from the field, or you're taking away from the population. So that's why it's a minus h. But it also takes account of immigration. So in other words, things coming into the system, or people coming into the system, if you just consider the h as just being a negative term, because then the negative just effectively cancels out, and you'll end up with a positive. So it's just adding. Okay. So what we're going to do is we're going to do it with the logistic model. So remember what the logistic model was? It was dn by dt equals Rn. And then we had to take into account of carrying capacity. Okay, so n over k. So that's basically the population kind of reaching its limited resources, and that's the logistic model. So the exponential model would be that. The logistic model now is with this extra term on the end to take into account. The population should level off after a period of time. Okay, and then of course we're going to take into account harvesting as well by sticking a minus h on the end. Okay, so effectively what we're going to try and do is try and solve this. Now we can solve it exactly, using exact method, but it's a bit tricky. So what we're going to do is we're actually going to do it by a far nicer method, which is phase portraits, just effectively drawing a picture, because phase portraits will nearly always work, hopefully. So what we're going to do first of all is break down the barriers, get rid of these brackets. So Rn is equal to Rn squared, minus Rn squared over k minus h. Okay, and I'm just going to rewrite this in a slightly nicer way. So I'm going to rewrite it as, what I'm going to do is I'm going to stick minus r on k, n squared at the front, so this term at the front. Okay, so we write the highest power at the beginning. Okay, plus rn, and we're going to have minus h, and that's fine. Okay, now what we're going to do now is we're going to basically say, well, first thing we need to do with the phase portrait is that we need to find the equilibrium points. Remember what the equilibrium points were? They're just the same as stationary points, so we set them equal to 0. Okay, we set the rate of change equal to 0 because a stationary point is the point on a graph or point on a function where the function isn't changing. So in other words, where it's not changing, then the rate of change is equal to 0, the gradient is equal to 0, and that's basically what we're saying here. It's just A level. So remember, stationary point, equilibrium point, it's the same kind of thing. Okay, if you're in equilibrium, you're stationary, you're not moving either way. Okay, so we set it equal to 0, so in other words, we say r minus r on k, n squared, okay, plus rn minus h is equal to 0. Now I'm going to tidy this up a little bit because I'm going to make use that it's set equal to 0 by the other side. So in other words, I can multiply this left-hand side, or divide this left-hand side, by whatever I like. And it won't affect the right-hand side now. It won't affect the right-hand side because it's just 0. If I multiply and divide it by anything, multiply and divide, 0 by anything, it's all still going to be 0. Okay, so I'm going to actually get rid of this minus r on k at the front. So I'm just left with a nice n squared at the front. So if I multiply through by minus r on k, what do I end up with? Sorry, I don't mean multiply through by minus r on k. What do I mean? I mean divide through by minus r on k. So in other words, I get rid of this. Okay, so I just get rid of this. So if I divide through by minus r on k, that's the same as doing minus r on k, so minus k on r, times rn, and then again minus k on r. Okay, so I'm just multiplying through by the inverse of that. That's the same as dividing through by it. That's going to be equal to 0. Okay, so what's this going to become? They're going to cancel, so I just end up with minus kn. Okay, this has become a, there's still an h there, isn't there? This is going to become a positive. Okay, so therefore this is what we get now. Okay, and this just makes it nice and easy. So, I mean, this is still general, okay, because it's just letters. There's no actual numbers. So there's no point trying to factorise it because there's no numbers to factorise, you know, which helps us to factorise it. So we're just going to have to jump in and use the quadratic formula. Remember what it is. It's x equals minus b plus or minus square root of b squared minus 4ac all over 2a, okay. So here, x is our n, yeah, because that's the thing, that's the main kind of variable. So we got x equals n. Okay, and the minus b, the b is going to be, oh no, let's go a equals, b equals, and what's c equals? So what's a equal? Well, a is equal to 1, okay, a is equal to 1, because that's just the coefficient in front of the n squared. Okay, b is equal to the minus k, b is equal to the minus k, and the c is going to be equal to this whole term on the end there. So it's going to be equal to kh upon r. Cool, okay, so now we can just use that to find out what the quadratic formula is for that. So it's going to be n equals minus b, so it's going to be minus k, so it's going to become a positive k, plus or minus the square root of b squared, so it's going to be minus k all squared, so it's going to become k squared, right, minus 4ac, so it's going to become minus 4 times a, which is 1, times c, which is k on r. So there we go. That's all going to square root upon 2a, so it's 2 times 1, so that's over 2. Okay, so what are our equilibrium points going to be? So I'm going to call my equilibrium points E1 and E2. So my first equilibrium point is when we take into account the positive square root, so it's going to be k plus square root of k squared minus 4k h upon r, all over 2. And the second equilibrium point, E2, is going to be the case when we have a negative here. So k minus square root of k squared minus 4kh upon r all over 2. Okay, so there we go. Those are our two equilibrium points. Cool. So, okay, we've got a quadratic going on. Okay, so what do we need to do is we now need to consider this discriminant inside the brackets. We need to consider this discriminant, this k squared. So what's our discriminant? I'm just going to call it delta. Okay, our discriminant is going to be the thing inside, not the brackets, inside the square roots. K squared minus 4kh upon r. Okay, so this is what a discriminant is equal to. And we need to consider the three cases. So in other words, when discriminant is greater than 0, when the discriminant is equal to 0, and when the discriminant is less than 0. So when the discriminant is greater than 0, we end up with two roots. And those two roots are E1 and E2. Okay, when the discriminant is equal to 0, we end up with one root. Okay, we end up with one root, so in other words, when E1 is equal to E2, okay? And when it's less than 0, we end up with complex numbers. So there's no equilibrium points. There's no equilibrium points, and because, you know, there are no equilibrium points because they're complex numbers. Well, complex numbers have no place in, you know, because what we're dealing with here is a mathematical model of a biological situation. Well, the biological situation is in the real world, so if you like, complex numbers don't really have a place in this model. So that's why we say there's no equilibrium points. Okay, so when the discriminant is greater than 0, in other words, we have both of our equilibrium points. When the discriminant is equal to 0, E1 is equal to E2, and it's just going to be, in fact, that's going to be equal to k on 2, isn't it? Going to be equal to k on 2, because if we make the discriminant equal to 0, it basically just disappears, right? So we're left with k on 2. Okay, E1 and E2, so we end up with E1 and 2, and then we're going to end up with no equilibrium points. Okay, so let's try and draw the different cases. So in other words, when the discriminant, so let's try and draw the different cases. So let's draw 3 graphs out. I'll draw this out. So okay, this is just a quadratic. So the case when discriminant is greater than 0. So case when the discriminant is greater than 0, we have two distinct roots. Okay, so E1 and E2. So let's plot them on. We have E1 here and E2 here. So E1 and E2. Okay, so in other words, what we have is this kind of thing going on. So it's a negative quadratic, remember. And we know it's a negative quadratic because of this thing here. So this is our negative quadratic. So dn by dt is equal to this negative quadratic term at the front here. This negative quadratic term. So we know it's a negative quadratic, so that's why I've drawn a negative quadratic in like that. Okay, we just remember we just multiplied through by all these different terms because we set it equal to 0. Well, this isn't what dn by dt is equal to 0. This is the case when dn by dt is equal to 0. In general, dn by dt will be equal to this thing up here. So it's going to be a negative quadratic. So this is what I'm drawing in now. So dn by dt, we have this thing going on. Okay. Then the case when the discriminant is equal to 0, we only end up with one equal root. So we end up with this thing going on. Okay, and then the case when discriminant is less than 0, we end up with no equal roots. So therefore nothing happens down there. So it doesn't cross the n-axis effectively. Okay, so let's consider different cases using a phase plane. So this is our equilibrium points now. This is our equilibrium points, no equilibrium points on here. So what happens with dn by dt? Well, to the left of the E1, so this is E1, this is E2, this is just our equilibrium point where E1 is equal to E2. Okay, to the left of E1, dn by dt is negative, right? So therefore we're moving to the left, all right? To the right, in between E1 and E2, dn by dt is positive, so therefore we're moving to the right, and to the right of E2, dn by dt is negative, so therefore we're moving to the left. Okay, so we can see now that E1 in this case is positive. Sorry, E1 in this case is unstable. Okay, and E2, because all the trajectories are moving towards E2, then therefore we can say that E2 is asymptotically stable. Now let's consider this case. Well, dn by dt, to the left of it, we are less than 0, so in other words we're moving to the left. Okay, this is E. To the right of it, we're also less than 0, so therefore we're still moving to the left. So in other words, what do we end up with? Well, we can just say that E is unstable. Okay, because this is unstable because the trajectories, to the trajectories to the right are moving towards our equilibrium point, but they don't stop at our equilibrium point. They carry on going, and we can see that by the trajectories to the left. Okay, and then to finally look at this case, we can hopefully see that dn by dt is always negative with this case. There's no equilibrium points. dn by dt is always negative because this graph falls in the negative part of dn by dt. All the dn by dt will always have negative values. Okay, so therefore we're always moving to the left. So in other words, in this case, we're always driven to extinction. The population is always driven to extinction. Okay, if the discriminant, so in other words, this where are we? This k squared minus 4k h on r, if that's always less than 0, then therefore we're always driven to extinction. So in other words, we've got our harvesting term too high. Yep. Okay. So let's try and interpret this in terms of our harvesting example. So what was our discriminant? Well, our discriminant was, let's find it, our discriminant was k squared minus 4kh upon r. Discriminant was k squared minus 4kh upon r. Okay? So in this first case here, we had the discriminant is greater than 0. So in other words, when the discriminant is greater than 0, we have k squared minus 4kh upon r is greater than 0. So let's try and rearrange that for h. So we'll take this on the other side. End up with 4kh upon r. Okay, divide through by k, multiply through by r, and divide through by 4. Okay, so when h is, so let's rewrite this out. So h is less than kr upon 4. Okay, there's a stable population size at E2, so there will be a stable population size. So providing we have an equilibrium, so providing we have an initial population that is falling to the right of E1, because obviously if it falls to the left of E1, then it's going to be driven to extinction anyway, okay, because E1 is negative. But providing we have a population size that's always going to be to the right, so it either falls in this region or over here, so our initial population is driven over there, we'll always have a stable population. Okay, so in other words, we can call this harvesting moderate. Okay, because there will always be, providing we have the condition that providing that n0 is greater than E1, so in other words it falls over here somewhere, then we have, providing our harvesting is less than this term, then we're fine. So providing n0 is greater than E1, so we've written down what E1 is. So this is the case, if we have moderate harvesting, then we're fine. Okay, But otherwise, if n0 is less than E1, n0 is less than E1, will always become extinct. Our population will always become extinct. Okay, so now let's look at the case when discriminant is equal to 0. Well, that's the case when h is equal to kr on 4. Okay, so when it's the same, this is what's known as critical. This is what's known as critical harvesting, because as you can see, at this stage our population is unstable, so we're going to go to the bottom, to extinction. But actually, it's not meaningful to draw any conclusions from that, because what it's saying is that in the exact case that our harvesting is exactly equal to this, which in general it won't be. In the real life situation, it won't be, because there'll be loads of different factors affecting, our population. Okay, so just to basically turn around and say, well, providing our harvesting term is exactly that, isn't meaningful in the real world. Okay, because, our model, in general, it's always better to be with a model extra cautious, okay, with the kind of conclusions of the model. Well, this is basically saying that providing we have a situation that is, there's not being affected by anything other than, there's not been, a species that's not being predated, okay, that there's not been any kind of natural disasters or anything like an oil spill, or if you're thinking about fish or something. There's not been any natural disasters. So basically we've got an absolutely sterile condition, then therefore we can take out exactly that much. But in general that won't happen in the real world. So we call that critical harvesting because in general it won't happen. So in general we don't really draw any meaningful conclusions. So we call it a meaningless example. So in other words, the next case which we need to consider is when the discriminant is less than 0. So in other words, when h is greater than kr on 4. Well, then you can see that this is what's known as large harvesting, or excessive harvesting. Yeah, excessive harvesting, because when it's greater than 0, we're always driven to extinction. We're always driven to extinction. There's no equilibrium points whatsoever, so we're always driven to extinction. No stable equilibrium points for all initial populations. Doesn't matter what the initial population is. Basically, if we're harvesting more than kr on 4, then we're always going to become extinct. Okay, so basically the harvesting value for the logistic model, okay, providing n0 is greater than E1, we can harvest less than kr on 4. So we can harvest less than kr on 4. So if we draw this kind of on a diagram of h, okay, so this is the harvesting number line. Okay, here's kr on 4. Okay, here we have critical harvesting. Okay, and that can't happen. Okay, because it's meaningless. Okay, if we're to the right of that, so in other words, we're harvesting more than that value, we're going to become extinct. We're harvesting too much. We're taking too much out of the system. Okay, to the left of that, we're okay. We're okay, providing n0 is got to be greater than our first equilibrium point, providing our initial population is big enough. Okay, if our initial population isn't big enough, in other words, if there's not enough there to start off with, then it will become extinct. Okay, so hopefully that makes a bit of sense.